Hello everyone, my name is Dr. Sanjay Prabhu. I am the clinical director of the 3D printing program called SIMPI 3D Print at Boston Children's Hospital. Thanks to the SPIN organizers for giving me this opportunity to talk to you about 3D printing, which is one of my favorite topics and I believe has already shown a lot of potential in enhancing clinical care and improving patients' lives, and I believe will continue to do so in the next few years. I have no relevant financial disclosures. Here is the outline for my talk. First, we will define medical 3D printing and describe how one goes about creating a 3D printed model. We will then talk about the key role of the radiologist in this process. Then we will see some examples where 3D printing helped improve care for the patient. I will then discuss some challenges one can expect to face when starting a 3D printing service and sustain this over the long term, and also discuss some potential solutions to these challenges. 3D printing is the process of creating physical 3D objects from a digital file. This entails creating a virtual design of the planned object in a CAD or a computer-aided design 3D modeling program for the creation of a totally new object. In the case of medical 3D printing, this entails using an imaging dataset acquired using a 3D scanner, a CT scanner, MRI scanner, ultrasound, or even rotational angiograms to replicate an area of the patient's anatomy. To prepare a digital file for printing, 3D modeling software slices the model into hundreds or thousands of horizontal layers. Each of these layers can be conceptualized as thinly sliced horizontal cross-sections of the eventual three-dimensional object. When the sliced file is uploaded in a 3D printer, the object is created layer by layer. The 3D printed object is then constructed using additive manufacturing technology. The object is built by laying down successive two-dimensional layers of material based on the digital slices until the entire object is created, as shown in this movie here. Optimal image segmentation is the most important first step in creating a 3D printed model. This is then followed by segmentation. Segmentation refers to the process of isolating structures of interest from the rest of the imaging anatomy. There are several software packages available to create files suitable for 3D printing. No single segmentation software tool is suitable for all images and application, and almost all tools have a learning curve. Once segmentation is complete, you move to the preprint process of the mesh model creation stage. Mesh model creation involves eliminating unwanted structures, removing artifacts, and fixing surface flaws. Other tweaks required at this stage include fixing holes to make the mesh watertight, removing discontinuous portions, and joining up elements artificially separated from the model due to segmentation. Finally, structures segmented from other imaging studies like MRI or hardware components can be then added at this stage. The refined mesh model is then sent to the printer in a variety of formats. The most common format is called the Standard Tessellation Language or 3D STL file format, which defines the surface geometry enclosing any 3D object as a series of connected polygons. The final step is post-processing, which includes curing, polishing, sterilization, and often the most time-consuming step is removing support material. The 3D printing process typically consists of depositing material layer by layer in a semi-liquid, liquid, or powder form and solidifying using light energy, electron beam, chemical binders, or heat, and allowing the model to solidify at room temperatures. There are different types of printers available, ranging from a few hundred to several $1,000s based on the intended use and capability. There are very usable 3D printers that can be used in a home or office setting for a few $1,000s. Let's talk about the radiologist's role in this whole process. I would argue that the acquisition of a high-quality volumetric data set is the most important step in creating a 3D printed model on any platform. If a structure is not imaged optimally or not included in the field of view, it's impossible to accurately segment and visualize it on a 3D printed model. The radiologist plays a critical role by optimizing the imaging studies, thereby enabling accurate delineation of the anatomical structures. The need to avoid imaging studies is vital in the pediatric population to minimize the risk of radiation exposure in case of CT or avoiding sedation for repeat MRI studies. As a rule, for CT, volumetric images acquired with slice thickness of at least 1 to 2 millimeters or lower are ideal for creating 3D models. Other parameters like larger voxel size and soft reconstruction kernels facilitate faster and more automated segmentation, enabling creation of smoother 3D printed models. But these would limit anatomical detail. For example, you can't see fractures on such softer kernel reconstructions. When using MRI, you want to have volumetric, isotropic data sets without significant gaps between slices. Accurate segmentation to delineate osseous, soft tissue, or vascular structures remains a relatively time-consuming process on MRI, even when using the most accurate software tools. Let's go to some case examples here. This is an example of a AVM, which our neurointerventionalists and neurosurgeons like to get copies of on 3D printed models. So here's a 3D printed model of this AVM blown up to a large size. This shows a very important advantage of 3D printing. Basically, you can produce these at various sizes, and it's very useful in pediatric patients where lesions can be really small, and seeing them in a very zoomed up state and from different angles and perspectives can help understand the pathology and aid treatment planning. We wrote about this experience in this paper involving just 4 cases a few years back as an initial proof of principle. We had patients with AVMs and Vein of Galen, and we showed that the use of 3D printed models was associated with a 30-minute reduction in operative time when compared with matched controls. We have had similar experiences with cases since then. This next example is a rapid printing of a 3D printed model during a facial trauma reduction case. This little girl was attacked by a dog and suffered severely displaced facial fractures. Her overlying soft tissue injury resulted in a very swollen and distorted facial tissue envelope. To overcome this challenge of performing open reduction and internal fixation in such a distorted field, the 3D printed model was printed on site within 15 hours of presentation. The bone fragments had been manipulated by the surgeon on the 3D printed model to achieve the reduction. In the process, Dr. Rogers Vazena, a surgeon, discovered there were areas of bone that were missing in the structural support regions of the face. She used this information to alter the surgical plan to include bone grafting and pre-contour the titanium plates so the comminuted fragments could be adapted to the precisely bent plates to achieve an appropriate reduction, rather than using the traditional approach of bending the plates to fit the bone in vivo. She said this plan would not have been possible without the ability to print the model on site. Again, we've done similar models since then. These are her exact words. She said she was able to arrange a neurosurgeon in advance to help her harvest the calvareal graft and also figure out why the pieces did not fit together. Patient-specific models are used even by experienced surgeons for pre-surgical planning. For example, this is one of our surgeons, Lawrence Collin, who has more than 25 years of experience in spine surgery. Once I created this model for scoliotic curve reduction in a patient with a complex myelomeningocele, he came back to me and he explained how it was easier for him to pre-bend the rods to the correct shape and size. He said the model helped him shape the construct to hug the bone and saved a tremendous amount of intraoperative time. We subsequently went on to do a few more cases together and published our experience in 2017, showing the markedly improved appreciation of the complex anatomy. And one thing he said was anomalous anatomy not mentioned on the official imaging reports was appreciated better on the physical model. The study also showed how the surgeon was able to pre-contour the rods based on the 3D printed model, resulting in reduced intraoperative fluoroscopy time and also reduced blood loss. We've also shown this similar results in patients with craniofacial reconstructions. Dental surgeons have been early adopters of 3D printing and have used these models to aid complex reconstructions for a very long time now. Groups including ours have published studies such as these, showing reduced intraoperative times, decreased procedural costs, and fewer complications when 3D printed models were used to plan complex pediatric craniofacial reconstructions. We actually showed time-based cost savings of almost $1,000 in these procedures, with almost a 31.3-minute reduction in operative time in similarly complex cases. Using 3D printed models to study anatomy and pre-planned procedures has several patient-related safety benefits. First, using them preoperatively to rehearse procedures and pre-contour hardware and implants reduces the intraoperative variation from the initial surgical plan. As such, this has the natural effect of decreasing the operative time and thus anesthetic time. This has been shown for a variety of surgical specialties. At Boston Children's, we've shown it for neurosurgical, neurovascular, head and neck, spine surgeries, and craniofacial reconstructions. Also, importantly, for craniofacial procedures, we have shown that their use reduces complications, likely due to better understanding of anatomy and decreased deviation from the surgical plan. I would extrapolate that you would see benefits like these in a number of surgical and perioperative care disciplines that are time sensitive, where understanding individual specific anatomy is essential. Here is a rubric just showing what I think is the key areas where 3D printed models play a role in surgical planning. Basically reduces uncertainty and fear in the surgeons and the team involved in the procedure. It also allows surgeons to develop new, efficient, and effective surgical approaches by practicing on the model and trying different methods out. It also improves communication between clinical teams and with parents, and reduces operating times, in turn reducing sedation, bleeding, and other complications. Another area where 3D printed models play an important role is surgical simulation and surgical training. Most surgeons are familiar with the phrase see one, do one, teach one, which embodies the concept of learning procedures by doing them. It fails to convey to trainees growing up in a system less than tolerant of mistakes and complications that learning is on a patient or a person. Patients who have entrusted their lives to surgeons and trainees have endured risks and complications as they serve as practice models for physicians learning and developing their knowledge and skills. An objective improvement in acquiring skill set to perform surgical procedures safely. With the introduction of 3D printing, we have a 3D printed model such as this, an ETV trainer that allows trainees to practice the procedure before trying this on a real patient. So this model is created using a mixture of 3D printing and casting processes. Our results in this paper we published showed that such models could help distinguish an expert from a novice when looked at by a blinded observer, and facilitates better learning. Here is how the model looks like on the surface. Let's talk about some of the challenges in creating 3D printed models. The technology has some limitations. The speed of creating a model is not always ideal. And also reimbursement is an important issue. There's also a need for finding clinical champions who will help take this forward in different hospitals, and also try and get funding and support from the hospital for this type of technology. One has to deal through hospital dynamics, and different interdisciplinary collaborations have to be developed over time, and it involves making a business case to the hospital as well. And finally, demonstrating the evidence to the hospital that this is useful and worth carrying on and sustaining over a longer period of time. The reimbursement strategy has been helped by the RSNA SIG, which has allowed development of a registry now to capture the 3D printed models being created. And we also have new printers on the market, making it faster and more accurate prints possible with the better colors, for example. And the new materials mimicking tissue texture and mechanical properties. This is the RSNA ACI medical registry, which is a pilot registry at the NRDR, which is now collecting data and allowing us to move towards reimbursement in the United States. Here are my tips for successful 3D printing. Involve the radiologist early, have constant feedback from the surgeon, and present the cases at multidisciplinary conferences, research and publish your results, and document patient care improvements to the hospital. The key takeaway I would say is 3D printing is a solution to a problem and helps advance patient-centric care. It has the highest value in these scenarios when you want to synthesize information from multiple modalities, or you're trying to deal with complex or rare disease, multidisciplinary collaborations, and planning novel treatment approaches. I would conclude by saying the 3D printing models have an increasing role in surgical planning, simulation, and education. Radiologists have a leading role in this field, and the skills needed for radiologists who are interested in this area is to anticipate surgeons' needs, engineering smarts, tailoring imaging studies, and ability to adapt very quickly to the surgeon's needs. Thank you very much. Please contact me with any questions or comments via email or Twitter.